Okay, everyone. Now we continue with exercise 2 for the Lagrange interpolation. You know that from previous exercise we have learned that how we apply the Lagrange interpolation to any function which is given in the question. And also we also discussed that it is not an obligation to use all the data set. If you wish to learn here, if you wish to find a value which is specified value for you, then you can also use polynomial whose degree 1 or polynomial whose degree 2 or so on. It's up to the data set points. But the thing that you need to focus on is that, when you are considering a data set, and if you wish to create a Lagrange interpolation to approximate to this data set, then you need to know that I will have here n plus 1 points. At most, I'm getting n degree polynomial, okay? So the degrees will be, when you are getting here n plus 1 points, it reduces to, it is giving you at most n degree polynomial. That's all. So you need to know these concepts. Okay, now we continue with exercise 2. Consider exponential x on an interval 0, 1. What should the minimum value of the number of nodes be to get cubic Lagrange interpolation which has an accuracy of 10 to the minus 6? Guys, you should know that when we are considering Lagrange interpolation, we know that I can create for n plus 1 points, I can create here nth degree polynomial, but at most n degree polynomial, okay? My polynomial has n degree, but maybe less than n. So, for this reason, we can consider here, let me sketch here, I can consider here a data set for me like a table, okay, let me write here, corresponding y values, so it can be x0, x1, blah, 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 xn, but let me write one more time, x2, and then dot, dot, xn, and maybe by using here 3 or 4 points, using 4 points, I can get cubic expression. But of course, my expression, my data set consists of n plus 1 points. Of course, it can be occurred, okay? So, let us discuss here. Cubic Lagrange interpolation means that your polynomial whose degree is 3. And we know that for this type questions, you are considering here how many nodes do we have here? How many nodes? So it is not specified for you like equally interval or not equally divided interval. So it means that we are considering for equally divided interval, I can also accept this one, okay? By considering accuracy, if it is not written here, unless it is given to you, you can also accept here to deduce here this order of this accuracy. You should also consider it equally divided can be acceptable for you. Okay, P3 give rise to E3. So E3, as we know from the definition, what was E3 in previous as a definition we wrote? I wish to show here. This is E3 if you are considering equally divided interval. So here is H means that what? B minus my right hand side minus left hand side divided by number of division. So totally it creates here n plus 1 points. Okay, we will continue to solve this question by considering this formula. So E3 was given h to the power 4 m4 divided by 4 factorial. So m4, m sub 4 denotes me the derivative, fourth derivative of my function with some psi. This psi, do not confuse with psi. This psi belongs to your interval, general interval we are discussing, okay? So here, when you are taking here fourth derivative of exponential x, it is giving you again itself, right? The derivative of exponential x, because it's again the same function. So you know that this is an increasing function. Okay, increasing function. It means that it takes its maximum value at the right side point. So this point gives rise to here maximum value for this function. Okay, I'm substituting here e to the power x, substituting 1 because of it is increasing function, so it is giving me m4 is defined as e. Okay, go ahead now. We are writing e3 from now on is less than h to the power 4, and we have deduced that m4 is e, so I'm writing e here, and 24 because of the formalization. Okay, I am knowing that from now on, this error, look at here guys, get cubic Lagrange interpolation, which has an accuracy of 10 to the power minus 6. So this is given like tolerance. So your error should be less than your tolerance, as you know. So this is my tolerance, here is my error. Okay. So when I'm writing them, from now on, I have just doing a rearrangement in my equation, which is my unknown here is h. So we will write down our h in terms of the other known things. Okay, we also know that what? H was here b minus a divided by n. So your E and A here, let me use my erase to show you here one more time, guys. So here, you know that your interval was given here. This is your interval. Okay, it means that, let me write one more time my interval here, 0, 1 with closed version. So it means that this is your A and here is your B. Because on this interval we discussed here our Lagrange interpolation. So now I will define here b minus a divided by n. How many points? How many points will be, what is your n? Okay, so by writing here your expression and doing your some calculations, you have obtained that here n should be bigger than or equal to 19.3454. Okay, so it means that minimum value means that you should take as an integer point. Of course, you are dividing because you're interval. So you should choose here minimum 19 iteration to handle with your problem to get this accuracy. Okay, so guys, now Lagrange interpolation is over and we will continue with Newton divided difference. To do this, let me open my new case for you and let's start to see how we understand here our Newton divided difference formula. Okay guys, I wish to give here some culture information about the Newton divided difference interpolation and Lagrange interpolation by a comparison actually. So in the Newton divided difference, please do not forget it. When you call a method by Newton, if you are considering here a method which also entitled by using the word Newton, the person whose name is Newton, it means that you need to use this one, you need to use derivative to accelerate your polynomial or your root finding or your solution of the system. This gives you some acceleration, okay? On the other hand, it should use here all the time derivative. So for this reason, we will continue with again polynomial approximation. Okay, so I mean we are having a data set and this data we are searching for a polynomial, a function which fits to my data set. So to discuss which fits my problem here, we will discuss here how we can create here the polynomial. This is the question actually. In Lagrange interpolation, we had used that our expression by considering polynomial, weights, which is calling LK, which are calling also the basis for us. Okay. Now we will see here. Okay. In other words, I can define some polynomial. For instance, we are considering here P1, okay? P1 means that whose degree is 1. So I'm considering here my degree is 1 now. So I can write my degree like from my data set, of course, okay? When you are using your data set, it is, for instance, x1, x2, x3. So it is starting with 1 and up to getting n plus 1. Then you are writing here by writing a1 plus a2 times x minus x1, which is my first component. Then you can also write down here, for instance, you are writing P2 can be written here a1 plus a2 x minus x1 plus a3 times x1 x minus x1 x minus x2. So this gives you recursive relation. Actually, you know that what is the recurrence mean? What does the recurrence mean? I think you know, but let me explain one more time. Recurrence in mathematics, we are calling recurrence if you have a relation which will be used in the next process. So the other or next approximation can be obtained from the previous one. So this gives you recursively relation. Okay, this is giving you a relation which is calling recurrence relation. Okay, so we will continue this process up to getting, of course, nth degree polynomial. You know that a1 up to here, we just classify here our data points. We know that, and the values of that data points we know from the experiment. But look at here, we didn't use any a2, or we didn't use, sorry, y1, y2, y3, and so on to describe here a1 and a2. We don't know them. So of course, there should be some relation between these constants, these coefficients, by the data set approximation, data set points, okay? So now our main purpose here is to describe how can we create here A1, A2, A3, and so on. Okay, here is our expression x1, x2, x3. So this is a table. This table will be helpful for solving this Newton divided difference interpolation case. So you have known that these parts will be known by the experiments, okay guys? So how can you find out here A1 and A2? After doing some analysis, so I'm skipping here to give the analysis, but you can also focus on here, for instance, to find out here A2, okay, or maybe you can find out here A1. You can describe here some expression here, or to find out A2, I mean here, when you are writing here x1, this gives rise to a1 itself. So a1 becomes your y1, for instance, okay? Because when you are substituting p1 x1, p1 x1 will become what? It gives you a1 from your relation. What I know about P1, X1 does not matter P1, P2, P3. So we know that Px1 actually should give me f of x1. So at node points, because our main contribution here for the interpolation to say that your polynomial, your approximation will give you the exact value at the node points. So this is the same thing. So because of this, this is corresponding to A1, for instance. How can you describe A2? If you take here both sides, if you take the derivative both sides with respect to x, then it gives rise to A2. So how can you define the derivative actually? So Newton says you here, okay, we have some choices to define here the derivative. Later you will see in detail to write down the numerical differentiation, but at this time maybe you may focus on here the derivative definition in calculus 1. The derivative definition in calculus 1, we said that you are writing here like the slope. The slope is corresponding to what? in this case, in the numerical methods, guys, we don't have here continuous space, of course. So when you are using the discrete space like you did in physics, you are considering here, instead of taking the derivative, you will focus on here the ratio, okay? Changing how can you find out the slope by 2 points, between the 2 points, how you can find the slope. It is the thing that we are using here. So this is called first divided difference. It is called second divided difference, then third divided difference, and so on. It is going as in that form. We can say that this table is creating a narrow triangle, okay? At the end, up to getting just 1 point, you will continue your process. Okay, I want to give here more precise definition for you. For instance, we said that here, this is my A1, here is my A2, and then this is my A3, and so on. We are taking. This is the first derivative, second derivative, third derivative, blah, blah, blah. We are doing here forward iteration, guys, because forwardly I am choosing forward. Means that first of all, I choose that one. I substitute from the top to the end. Okay? But when I are calling the backward means that from the last one, from the end to the top, you will go back. Okay, here you should know that, guys. I wish to erase this part because this is important again for you for your calculation. I wish to show something to you. Okay, when we are calling our expression, how can we find out the derivative? So the derivative can be observed that, you know, by 2 points, y2 minus y1, x2 minus x1. So this is giving me first slope. And then I'm considering here 2 points from now on. You have 2 points like this one, like the, you know, blue marker, blue point and the red point. Look at here, guys. When you are writing them, your second point minus first point, second minus first, divided by what? Divided by, so you please follow my pencil, okay? Here is my point. It is my, this is your intersection point, guys. The intersection point, now you choose the below part, below line that you can see. So this below line means that from now on, I will follow all the below lines corresponding to these points. So we are going to the point. Point is here. It was the intersection, so I'm choosing here my below point, below line again, okay? And I'm choosing here my point like x3. So this is corresponding to x3 here. Now, if you choose, let me choose from now on, let me choose here the purple, for instance. Okay, not this one. Now, from now on, we will focus on here our point, this one. If you choose upward direction, or upward case, then you will choose here the point corresponding. Again, all the time I'm using upward for the consistency, okay? So upward will be, I'm going to, what about my point corresponding? It is x1. So when you are writing it, this is the divisional form. You will do the same process for all expressions, okay? We will continue with our new expression. Let us continue. We will do this process up to seeing, guys, all the time we will do it up to seeing here just 1 point there should be. Okay, choosing the values y1, y2 minus y1. So I wrote it. Here is a1, this is a1, it is a2, this is a3. They are called here all coefficients, okay? Yep, we continue with here forward Newton divided difference interpolation. Okay, guys, it is time to see an example for it. An experiment is conducted on a laboratory and various values of this experiment are listed in the following table. Estimate the value y at blah blah point 35 by using forward Newton divided difference interpolation. Okay, let's go ahead here. Here is 0 point blah 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 1. So don't forget this is missing for my inside my domain. Because of this we are saying interpolation we are doing here. So I wish to consider here, of course we know that what this interval, it is not a oscillationary form. I mean oscillation means that 1 plus 1 minus 1 plus 1 minus version. So you know that this is the increasing data set for me. So my 0.35 will be, of course, will be stated over this interval, on this interval. Okay, now we are creating our table by considering the formula which is given in this table. Okay, let's do it. Subtracting 0.1210 minus 0 divided by 0.1 minus 0. So it is 1.21. Continue. Minus here 0.2258 minus here, it will be subtracted from here and subtraction divided by 0.1. You will do this process. From now on, here guys, I'm considering subtracting here. For instance, I'm subtracting 1.048 minus 1.210 minus divided by, now I'm on this point, okay? Look at here, I'm on this point. I choose the downward direction. Downward direction I'm choosing. Downward direction says me I am now y2. Corresponding, what is your x? X is here 0.2. Now, when I'm choosing upward, I'm using the upward directions by tick, okay? And again, I'm using upward. And then it is corresponding to the 0 point. So means that 0.2 minus 0. For instance, in this position, now I am using here downward direction. The downward direction I'm using, x representation I'm using. Then the downward direction I choose, the downward direction says me here I am, then it will be x4 minus upward direction corresponding to that choice here, and then I'm going to do 1.048, and again upward I'm choosing. Upward says me I'm here, so I should use here 0.1. So it means that you are subtracting them from each other and divided by here 0.4. So you will continue this process up to seeing here just 1 point. So I will continue this process, okay? And the final decision of star, which is I'm saying here star, so the answer is minus 0.1254. When you are writing your polynomial, guys, so it would be here 0 plus 1 point. I'm choosing for first forwardly, okay? I'm using forward iteration and choosing all the top point that I'm seeing in my columns. This is my first column, and I'm choosing first column, first row. This is my second column, first row. Third column, first row. Fourth column, first row, and fifth column, first row. Then I'm choosing all these points. It means that 0 plus this is a1, a2 times x minus x1, a3 times x minus x1 times x minus x2, and so on. So finally, if you wish to learn here what is the value as of this point on the Newton divided difference, then it will be here by the substitution you are getting here 0.3577. So what is your degree here? 1, 2, 3, 4. Most degree here is the fourth degree polynomial we observed. By using again 1, 2, 3, 4, 5 notes, we have observed fourth degree polynomial. This is again important. Okay, using the same data set, find second degree Newton interpolation polynomial to estimate the value. Again, the same estimation and again the same data set we are using, and trying to find out here again new estimation which is corresponding to the same value. But this is the thing, need to use second order. It is second degree, means that you should use three nodes, okay? 3 nodes. These 3 nodes will be chosen from the interval. Okay, we know that which 3 nodes I can choose here. Guys, because we are using the forward iteration, you should use here, you are listing you will put it into your interval. You should first of all determine where is the interval, where it is located. After putting it into that expression, so I'm using 1, 2, 3. 3 iterations, 3 points are chosen. I hope you have a question according to that choices, because you are asking to me, I think, what about this point I'm choosing instead of here point 2, point 1, point 2, point 5, may I choose point 2, point 5, point 8? Of course you can choose. It is not important, okay? But because we are choosing the forward iteration, because of this, I'm starting with that expression 1.21 and 0.5. So we will create again our table, okay? After putting here the table, we have observed that now this is my new A1, new A2, new A3. Do not confuse with the previous one, because we completed the previous question and it's over. So now we are creating new polynomial whose degree is 1. So I'm writing here again forward Newton divided difference interpolation. So I'm writing here x1 and x1, x minus x1 times x minus x2. They are multiplied by each other, and totally I'm substituting, instead of x, I'm substituting 0.35. So the answer is here. Okay, guys, let us compare the answers. So first estimation says us 0.3577, and second iteration says me 35.95 again. So guys, we can say that here, if we use all the data set, this is more better than the small part of the data set, because you are using your data set more efficiently. You utilized all these points. So this describes your behavior of the function more efficiently, okay? For this reason, if we have in your experiments, if you wish to get here a curve which fits your data, if you wish to interpolate something, please try to use all the data sets. Of course, this data set point sometimes can consist of some outliers, okay, outliners. Then you should use some statistical process to eliminate, to get here the better approximation. To get the better approximation, you should eliminate something, and you should set your data set which is appropriate for the approximation. So this thing here, you are combining all the mathematics here that you have learned in this process. So I'm closing this section, and for today's this week's class, this is over. But if you have any question, I hope there is no more question for you. If you have any question, you may ask it to me by email. On the other hand, guys, if there are some problems in your expressions to understand it, you can also, if you decide a common decision I'm talking about, if you decide there are some questions and we couldn't understand something blah blah, then we can open a leave course, okay, on Canvas if you wish, or we can also continue on that expression. I can take your questions on the leave course. So in this week we don't have MATLAB class. I think next week we will not have MATLAB class, but after 2 weeks, 2 weeks later, we will see a MATLAB course, which will be dedicated for 3 hours, okay? So I'm saying 3 hours, of course, 3 courses, let me say, 3 lectures. So guys, see you next week. Have a good week. Study, study, study. Okay?